Hello, my name is Ken Millard, and this is Solving Bejeweled with Genetic Algorithms and Wisdom of Artificial Crowds. So some of the things I'm going to talk about today: genetic algorithms and wisdom of artificial crowds. What are they, and how do we attempt to use them to solve this problem? The Bejeweled problem itself, I'll go into a little more depth, and then the implementation that I did, the actual program that I created to attempt this, the results of that, and then also lessons learned. So the problem, Bejeweled. So Bejeweled is a tile matching match 3 game. Similar games include Candy Crush Saga, Puzzle Quest, a bunch of different casual games that are fairly that are very popular on Facebook. The gameplay is that the player selects 2 gems to swap on a board, and these 2 gems, the swapping of which, if it creates a match, if it causes 3 or more gems of one particular color to all be the same, either a horizontal or vertical line, then those disappear and explode. And then in most cases, new gems fall from the top, like as if by gravity, filling in all the empty spaces. So, and matches can be are at least 3 gems. However, matches with more than 3 gems are better and receive more points. And we see this in the fitness function of our genetic algorithm, which I'll go into more later. So what is a genetic algorithm? A genetic algorithm creates a random set of possible solutions, a population of sets, and then combines them to form new solutions. So those sets are sorted. So they're sorted by their fitness. So how good each one of those possible moves is in this case, and then the best ones are mated together all the way down the line to the worst ones to try to find new possible solutions. However, the best solution is always retained in this particular implementation. Excuse me. The genetic algorithm repeats this process over and over again through a set number of generations, in this case 10 generations, which was a restriction due to performance issues. And the after the set number of generations is done, then it looks to find the best solution that remains in that population, and that is the solution that it chooses. If that solution is not valid, which towards the end of each run of the program that tends to be the case, then it attempts itself again and again until it fails out a total of 5 times in a row. So it does a best effort to try to find a solution that creates a match of 3 gems. So wisdom of artificial crowds, essentially it's a meta-heuristic algorithm. It is a post-processing technique that is applied to, in this case, to the solutions, the population of a genetic algorithm. In short, essentially what it does is it looks to see what the most popular answers are in the genetic algorithm, and it attempts to see whether or not the most popular answer is better than what is listed as the best answer in this particular implementation. Wisdom of artificial crowds is based off of wisdom of crowds, which is a principle where they had a random group of individuals back in the 1900s try to guess the weight of a cow, and then took all of their answers, aggregated them together, and then compared those with answers from experts, and found that the average of all those guesses tended to be better than that of an expert. So wisdom of artificial crowds is an artificial intelligence version of that attempts to find that attempts to play upon that same natural tendency. So implementation, solver engine. So essentially it's a Bejeweled clone that plays itself versus allowing any user input. It uses a couple of different strategies to try to solve the game. So essentially it keeps a copy of the original random board, so it generates that, and it's randomized, and then it saves a copy. But then it takes the original and it applies the first strategy, which is a greedy first available search. It's essentially a brute force algorithm that looks for the first legal move that it can find. And once it finds that legal move, it takes it, and then it does it again and again and again until it runs out of moves. And by running out of moves, it attempts to find a move 1,000 times in a row, and if it fails, then it tells you, okay, it must be finished, and it tends to have pretty good results. Once that is finished, then it takes that saved copy of the board, replaces the board with that one, and then it attempts the second strategy, which is a genetic algorithm and wisdom of artificial crowds hybrid algorithm. In this case, the genetic algorithm uses 50 sets in the population and applies that over 10 generations before selecting each move. So essentially every move that genetic algorithm and wisdom of artificial crowds algorithm takes is a result of 10 iterations of this crossing over and mutating and everything that is part of that genetic algorithm, and then applying the wisdom of artificial crowds. So, and lastly, throughout this whole process, it gathers information about the choices that are made, and then pipes those over to a series of graphs that are created at the end of the process. So here are a handful of screenshots, as you'll see, and I'll actually bring up the solver here in a moment. But in this case, the gems are represented by letters because at the time, my daughter is actually still very into letters, so I decided to use letters instead of pictures of jewels. But in this case, you can see there are two blocks there, a red block and a blue block. This was more for testing purposes, but it shows the red block being the number 1, which is the one that where the cursor is, as if the user were picking a box, and the blue box is where that gem is being swapped to. So it allows us to see, and you can actually see in the bottom left in the first picture where it says select and it says 3-0, which it would be 3 over from 0, so, and then 0 being the top line, so that's where the cursor is. And you can see the swap direction is down, which shows you that, okay, the 3-1 is where that gem, that one that you have selected, is going to swap to. It also keeps track of the turns placed as well, just so you can kind of get a good feel for that. Also, in these screenshots, I included a handful of other items. First one being the solution found. So it's either 1 or 0. So 1 means that there was a solution found, 0 means that there was not. In this case, there was solution found. This is somewhat atypical of the solution of what is typically found, and normally they're fairly close, but in this case the brute force is what I called it, algorithm. The greedy algorithm actually played about 32 turns before it ran out of moves, versus the genetic algorithm, which ran out of moves after looks like about 7. And And then the last picture there is the time to solve. This was very representative of the amount of time that it took to solve. So the brute force algorithm, because it does not actually have to determine the fitness of the move, it just sees a move, and if it's legal, it takes it, and that's it. Then in this case, it takes much less time. So it took an average in this case of 0.15 seconds per move, with a little spike there. Whenever it's a little more difficult, there's less moves to make. Versus the genetic algorithm, which took about 3.6 seconds to solve, which was fairly representative of having a population of 50 and 10 generations. Having only 30 in the population reduced that down by 1 second, but you could assume safely that the performance would get much worse and much worse as that population increased. So let's kind of open up a few things. Start off with, let's look at our project so we can kind of get a good feel of what it looks like. So here we go. As you can see, doing some kind of interesting things there. So each one of these separate lines is the brute force algorithm, which goes first, finding another move. So you can see that it's kind of skipped past a couple of moves that would have given it more points, but it doesn't care. It just looks for the first move. So in this case, it actually runs through 1,000 different tries before it gives up. And it tends to be fairly good. It tends not to leave anything unfinished. You look around on the board, I don't see any moves available. So mathematically speaking, it's very unlikely that it would miss a move those many times. But so that's where this algorithm stops. So now you can see that it played about 16 turns, and it has run out of moves. So it resets the game board. Now it's using the genetic algorithm, which you can see it is each generation almost takes as long as it took for the entire first moves of the other algorithm. So it runs through this fairly slowly, but it does do some interesting things. It tracks the cursor location and as well as the direction of the swap, and then also the fitness of that move. So in this case, all the moves so far have been equal to 3. So all of them have been a swap of 3. No swaps of 4 so far. And actually, because of the size of the board, swaps of 4 are actually somewhat unlikely, statistically speaking. So as you can see, by this point, the other algorithm had already ran through about 6. Had run through its full courses. So, but in this case, it's still kind of running. It's actually approaching the point where the other algorithm stopped. So there are a couple of things that make this somewhat difficult to make even. Though I did make an attempt to actually keep these things as even as possible, to try to level the playing field. A lot of the problems are that the blocks at the top are changed randomly. So changing them. So after the first several moves, the board is very different than what would have transpired from the other one, even if they take the same moves. So that's somewhat of a consideration in this case. Beyond that, tried to level the playing field as much as possible to try to get a good representation of how effective each algorithm actually is. So you can see it's still running through pretty well. Still say a handful of matches. I see maybe 2 left. So yeah. Oh good. It should have, yep, a fitness of 6. So it could have chosen, that was actually a good representation of what, when it chooses the higher scoring. In that case, it chose the move of swapping the one that created 2 sets of 3 instead of swapping and finding the 4, which was also that case. So, and it actually has found a couple of ones that are a little more fit. So this one is actually playing through quite well. But again, once you get past the first several moves, it's somewhat unlikely that you can really evenly compare the results of one algorithm to the next. I think we're not quite at the end, but getting close. I see one more, depending on what happens. Yeah, it's not finding that one swap in the middle. Well, okay, I guess there were a couple. But anyway, to get back to the explanation, we'll let this play out in the background, but we'll get into some of our results here. So one of the things I found, and it's obvious from actually watching it run, is that the greedy algorithm is much faster at finding a quick answer. The greedy algorithm took less than 0.25 on average seconds to find each match, and then to take it and then move on. It's mostly because, again, you could see that the genetic algorithm, Wisdom of Artificial Crowds, was actually testing for fitness, which was actually where most of the performance issue came about, because it's somewhat more complicated than just determining whether or not the move is legal. Genetic algorithm took either about 2.5 whenever I was first starting to test with a population of 30 and 10 generations, or it takes somewhere closer to 3.5 seconds per move for a population of 50 and the same number of generations. Greedy algorithm tended to be better than about finding some solution regardless of its fitness. However, genetic algorithm is usually better at finding a solution with a higher score than the brute force, because most of the time it'll just ignore the fittest solution in whatever one it finds first is going to do it. So we'll see whether or not it's still running, so we'll go ahead and we'll just continue. So some of the lessons learned. Performance of the genetic algorithm is hindered by how my implementation checks for matches. So the difficult part is that essentially it creates a copy of the board and then it lets it run through that match to see whether or not that one or the one or afterwards, whether or not it creates more matches. So this kind of created a pretty large performance problem because it's essentially copying a fairly large object with images attached to do this fitness check, and it does that fitness check across the entire population for each generation. So each one of those, that's 10 generations times 50 in the population. That's 500 times that it regenerates that the board object. So it's something that I would have to re-engineer to increase the performance of it, and with that it would have a direct result on the genetic algorithm having better performance. Now the genetic algorithm, there's another issue in general with genetic algorithms and Wisdom of Artificial Crowds with this, where it isn't really the most appropriate solution to this problem, mostly because of the variables that are involved in a Bejeweled, like a match 3 style problem. In this case, there aren't a lot of variables to splice together. Like I've seen some other genetic algorithms where it's essentially like creating different cars and different things that, over time it creates these things with different size wheels and different size vehicles and things, trying to traverse like a different landscape or something. But in this case, there are very few variables, and there's really only two. There's the position of the cursor, which the x and y are kind of bound together, so you can't really separate those two without it essentially being completely irrelevant to the original. And then the match location, or the match direction, either up or down or left or right. However, this also creates its own issues because those are really bound together as well. So matching in one direction versus another direction actually creates a whole different solution that has almost no bearing on the original swap that was being planned. So it's maybe not the best solution for this particular problem. However, it is a very interesting study. Okay. So our stuff is finished finally. Wow, that actually ran a long time. It's somewhat non-representative of the solution or what I've found. However, you can see it found a couple of higher matches down here. So these are some of the things that it generates at the end. It generates fitness scores for just the genetic algorithm. Otherwise, trying to avoid the performance hit in my brute force algorithm. So in the next one, you can see solutions found. Basically, it found solutions until it didn't for the genetic algorithm, for the brute force algorithm. However, genetic algorithm, you can see it has points where it fails to find it, but luckily it fails less than 5 times, so it really pushed its way through. Somewhat unrepresentative of what I saw, but it turned out very well. So in this case, one of the reasons why wisdom of artificial crowds, and that was really to my third point on the lessons learned, was it tends not to use the solution because the solution is already so even if the best solution is the most popular solution in the crowd, then it tends to then that solution has already been chosen by the genetic algorithm because it always chooses the best. So having the wisdom of artificial crowds look through the total number of choices in the set and finding the most popular, it'll always be less than or equal to that one. And it's because really, unlike some other things like TSP where you have a lot of variables and you can kind of swap them all around. In this case, there's really only 2, and you can't really change them without completely changing the fitness of the set. So in this case, that wisdom of artificial crowds has the same limitation in this case as genetic algorithm in solving the Bejeweled problem. So this is what I meant with time to solve. In this case, it actually took a lot longer, probably because I have a lot of things open, which does affect the performance. However, it took somewhere about 5.87 average time to solve for genetic algorithm for the brute force, about half a second. However, in this case, somewhat of an outlier, but the genetic algorithm actually ran for 77 turns. In my other experiences, it tended to be somewhat similar to the brute force. However, as I continued to tune it has provided some some improvements. For example, one thing that I've done recently in my testing is actually changing it so that it has to fail 5 times in a row versus just a total of 5 times. So that way, as you could see, it fails fairly often in the middle, but if there is a match possible, it tends not to fail those many times in a row. So making that change, I think it is contributing to this increase in performance. So those are the primary lessons learned. Overall, I would say that the Bejeweled problem is not easily solved by a genetic algorithm. Brute force tends to be a fairly solid solution. However, it is an interesting study, and it is an interesting method to attempt to try to solve this difficult problem. So that's it for my presentation. Thank you very much, and have a good day.